One tensor core runs 64 fused multiplies inside a single clock cycle. That clock is a heartbeat lasting under a nanosecond. And inside that flicker, a wall of switches does the math your AI runs on. Every AI model you touch is billions of these tiny multiplies stacked up. Ask a chatbot one question and switches flip trillions of times. So how does a speck of electricity become matrix math? If we can't see that chain, GPUs stay magic. This video makes the whole thing concrete, one transistor to one tensor core. Start at the bottom. The whole machine is built from one part repeated, a switch. A transistor is a voltage-controlled switch. Push enough voltage onto its gate above a threshold and current flows through, that's a 1. Drop below the threshold and it blocks the current, that's a 0. No moving parts, no lever. Just voltage deciding yes or no. Now the scale. A modern transistor's gate is roughly 3 to 5 nanometers across. That's a few dozen atoms. Billions of them fit on a chip the size of your thumbnail. Here's the part people miss. Flipping that switch is nothing exotic. The gate is a tiny capacitor, a bucket that holds charge. Switching just means charging or draining that bucket. Electrons rush in, the switch turns on. Electrons drain out, it turns off. That motion of electrons is the electricity becoming computation. Nothing is being understood. A voltage is moving charge, and the charge is opening or closing a gate. Hold that picture. One switch on or off. Everything above it is just switches wired together in clever ways. One switch is boring. Wire a few together and they start to decide. Connect transistors in patterns and you get logic gates. An AND gate outputs a 1 only when both its inputs are 1. An OR gate outputs 1 if either input is. A NOT gate flips 1 to 0. That's it, 3 simple rules all built from switches. Now stack those gates into something that counts. The smallest piece of arithmetic is a full adder. It takes 2 bits plus a carry bit left over from the column before and it outputs 2 things. A sum bit and a new carry bit. Adding 1 plus 1 gives you a sum of 0 and a carry of 1, exactly like carrying the 1 in grade school addition. A full adder is roughly 28 transistors wired together. And that is the atom of all arithmetic. Look closely and there's no calculator inside, no understanding of numbers. It's pure switching. Voltage in, voltage out, following those 3 logic rules. So how do you get from adding one column to multiplying whole numbers? You chain them. That covers adding. Now the why is how adding becomes multiplying. Multiplication is just repeated shift and add. Think of long multiplication by hand. You multiply by 1 digit, write the partial answer, shift it left, then add all the partial answers up. A chip does the same trick with adders wired in rows. Each row makes one partial product. The next row shifts it and adds it in. Chain enough adders and you have a multiplier, no new magic, only more switches. Here's the single operation that matters most. Take 2 numbers, multiply them, and add the result to a running total you're keeping. Multiply, then accumulate. Engineers call it a multiply-accumulate or MAC. 1 multiply, 1 add again and again. A 16-bit MAC does this on numbers up to 16 bits wide. Why care about this one operation? Because neural network math is overwhelmingly max. Every artificial neuron takes a weight, a stored number, times an incoming activation and sums thousands of those products. Weight times activation add to the total. Do that a few trillion times and you have a model's answer. So the whole game becomes, how many MACs can you run at once? Here's where the tensor core earns its name. 1 MAC is 1 multipliad. A scalar core, the ordinary kind, does 1 MAC per clock tick and moves on. That's the bottleneck. A tensor core throws out that 1 at a time rule. It's a hardware grid of MAC units, wired in a shape engineers call a systolic array. Think of a bucket brigade, where each unit passes its number to the next in step. A common block handles a 4x4 by 4x4 matrix multiply. Computing D equals A times B plus C. Multiply 2 small grids of numbers, add a third grid in one shot. Count the work, that block does 64 multipliads in a single clock. 64 where a scalar core did 1. But raw count isn't the real trick. As numbers flow through the grid, each one gets reused by many MAC units on its way through, read once, used dozens of times. That reuse is the whole point. Fetching a number from memory costs far more energy than the multiply itself. By passing data cell to cell instead of refetching it, the tensor core stays fed and burns less power. That's why it's both fast and efficient. So what happens when you don't build one of these, but hundreds? Now zoom out to the whole chip. A single modern GPU doesn't hold 1 tensor core. It packs hundreds of them side by side. They're clocked near 1 to 2 billion ticks per second. And on a busy AI job, they're all firing every single tick. Let's multiply the whole thing out. Each core does 64 multipliads per clock. Hundreds of cores run in parallel. And there are on the order of 1 billion clocks every second. Chain those 3 numbers and you land in the hundreds of trillions of operations per second. The number sold on the box as TFLOPS, trillions of these math operations each second. That's the raw output of a wall of switches flipping in lockstep. And here's why this exact machine, and not some general-purpose chip, runs modern AI. Every layer of a transformer, the design behind today's language models, boils down to one job: multiply a big matrix of inputs by a big matrix of learned weights. That's a matrix multiply, the precise thing a tensor core is built to do. The hardware and the math are the same shape. Build a chip that does matrix multiplies absurdly fast, and you've built the engine every large AI model runs on. Now trace the whole chain back in one breath. Electrons rush in and charge a gate. That charge flips a switch, a 1 or a 0. Wire switches into a full adder and it counts. Chain adders into a multiplier, then bolt on a running total, and you have a Mac. Tile 64 Macs into a grid, and you have a tensor core. Tile hundreds of tensor cores onto a die, run them a billion times a second, and you have the model's answer. Every link is just switches feeding switches. The promise up top, 64 multiplies in one clock, turns out to be nothing mysterious. It's a wall of adders wired to fire all at once, on one heartbeat of the clock. There is no thinking metal here. AI math is electricity moved through switches, at a scale and speed the human mind can't picture, but the diagram can. That's the box open. So that's the throughline. One transistor charging like a tiny bucket, all the way up to one tensor core doing 64 multiplies in a single clock. Same switches, just stacked. But a wall of cores this hungry has a new problem: feeding it. Those cores can only run flat out if numbers arrive fast enough, and that's the story of memory bandwidth. That's the next box we'll open.